Yeah. Right. Now, yeah. Thanks, Kevin. Yeah, I have written this up, and I'll post this in the book. Just some of the reasons that it makes a lot of sense to study string theory. There are others. Any model in physics, well, first off, it's just a model. It's all models. You know, we don't have, you know, direct knowledge of the world, right? We build models and we check how they correlate. String theory is capable of suggesting experiments, and this is what any model should do. It gives us some things to look for that may or may not be there. And whether or not they tend to confirm string theory, they give us the knowledge from the results of those experiments. There's been a lot of mathematics that come out of string theory. One of the most important things is the idea of dualities. And there are a couple of ways you see dualities in string theory. It turns out that for topological reasons, I think, you know, it initially was thought to be a matter of boundary conditions, but it seems to be a bit more complicated than that. I wanted to show you why there were 5 types of string theory, but they're all sort of different. But there are dualities that connect them all, called S and T dualities. Which is it? Well, one of those dualities shows that of these 5 types of string theory and one more, a supergravity theory, a 10-dimensional supergravity theory, certain pairs of those are related by just a difference in their perturbation theory. If you expand one of those in some parameter, expanding it in the inverse to that parameter gives the other string theory. So that these two are really just the same string theory looked at from a different thing being strong and weak. They're essentially the same theory connected by these perturbative expansions. The other duality that's come out of this is related to momentum. If you compactify a string theory on a circle, then the string can wind around that circle an arbitrary number of times. Also, you find that the momentum in that direction is quantized. And if you interchange the momentum quantum number with the winding number, it turns one string theory into another string theory. Okay, that's weird. Well, that's maybe not so weird because it's probably a symmetry in phase space. That's in a biconformal space, that's exactly what complex conjugation does. It interchanges momentum and or a momentum translation and a position translation. So, you know, this is not as bizarre symmetry as it seems. In any case, it's a new sort of duality that people weren't aware of mathematically, having these very different looking things related by these sorts of symmetries. Possibly the most important duality that people have hit on, and this I think is the subject of Oscar's research. He works with the ADS-CFT conjecture. ADS stands for anti-de Sitter. That is well, de Sitter, anti-de Sitter, and Minkowski space are all of the maximally symmetric solutions in general relativity. So when we talk about ADS, we're talking about a gravity theory formulated on anti-de Sitter space. CFT refers to a conformal field theory. And if you look at the ADS gravity theory and transform to the infinite boundary of that theory, it turns out to be equivalent to a certain conformal field theory on that boundary. And this is seen to be rigorous in certain cases. I think the four-dimensional case, it just works, but conjectured to hold more broadly. May or may not, but it suggests that there's a relationship between something like SU3, you can have that's a conformal field theory, and gravity. So in principle, you could seek solutions in quantum gravity by looking at quantum SU3 theory, or vice versa, depending on which you have more solutions for. So, this is an entirely new thing mathematically, this kind of correspondence between different sorts of field theory. There are other things, not theory. We've learned a lot about what are called Calabayau spaces. There are spaces called Kähler manifolds that, in addition to a metric, have symplectic structure and complex structure. Examples of these include biconformal spaces and double field theories, all of which come up in the study of string theory. A Calabayau manifold is a Ricci flat Kähler manifold. So Kähler manifolds are these very nice things that have symplectic and complex structure. If you solve the vacuum Einstein equation in one of those, it's a Calabayau manifold. So there's solutions to vacuum general relativity. All right, so what people think is a way to go from a 10 or 11 dimensional string theory to 4-dimensional spacetime is that the additional 6 dimensions, say for 10-dimensional superstring, are compactified onto a Calabayau manifold. So it satisfies the gravitational field equation, but gives a small compact space for 6 of the dimensions, small enough that we don't see it except for certain symmetries. And those symmetries could survive perhaps as the standard model, or the standard model could arise from other symmetries of string. So the understanding of Calabayau manifolds, that's interesting to mathematicians, in and of itself. Well, there are billions of them, 6-dimensional Calabayau manifolds, complex spaces, but there are starting to be substantial classifications of those geometries. And the motivation for that may be string, but the purely mathematical interest in these classifications is substantial. And, I'm listing these mathematical results. This is just scratching the surface. There's a lot that has come out of the exploration of string theory in that sense. In any case, advances in physics come in fits and starts. We're looking at the development of string theory under a microscope. From year to year, there may be an advance, or there may be slow progress, but at any time, there could be a substantial shift that gives us a slightly different theory, or a magical way to solve problems in string theory, a way to predict the standard model from string theory. And any of those things are something we haven't thought of yet. Could happen that makes string or string-like models lead us to an even better model, or a successful implementation of this one. So, various reasons to think about string theory. I think the thing I find most compelling is that it is the only quantum system I know that contains the Poincare group among its operators in its free algebra. But any of these other things might justify having a look. Okay, so let's move on to something a little more concrete. The description of the string world sheet. And this begins with position of a string in space-time. So here we have space-time, and we've got a whole bunch of orthogonal coordinates in whatever dimension you choose to do this. And it turned out to be necessary to think about this in arbitrary dimensions because it works better in certain dimensions than others. And some mathematical things do. But okay, in this space, we have a position vector x, and we would like that to point to, at some time, we want to point to a string, a finite extended object, mathematically idealized like a particle, but it's got extension in one dimension. And we parameterize that dimension by sigma, and then as it moves along in time, any point on the string has a world line with a proper time, and so we can assign a proper time coordinate to each point on the string, and that comprises the world sheet. So this position vector depends on two variables, sigma and tau, and this is the principal field of our theory. Now, we want to use that to, to do two things. We're going to want a field equation that says that string does what we know it does. We've solved the, if we call this displacement u, well, we know that a string has normal modes, and we may have worked through this model in classical mechanics last fall. I don't remember, but it's a straightforward classical mechanics problem. You get modes that have any integer number of peaks and nodes, and it will be described by an equation of this form. The displacement u will change in time and change if we have x going this way, second derivative of x. And so this looks basically like our scalar field. So we more or less expect these to behave like a scalar field. This v in the classical model depends on, I think it's like the square root of the tension divided by the mass per unit length of the string. Now, our space-time strings do have a tension because you can imagine the string rotating end for end that tends to stretch it. That produces a tension in the string. So our strings have tension. If we have a closed string, it can be spinning around, say, the central axis, and that produces a tension. So these strings can have a certain tension in them. Tension might also be produced because on the ends of the string, we imagine there to be certain quantized charges. And those charges might be attracting something. Well, that's not exactly what happens because all forces, remember, come from strings making and breaking. But there are quantum numbers associated with the ends of the string. The first use people have found of a two-dimensional membrane like this in fundamental physics was actually due to Dirac in 1962. He envisioned a spherical membrane oscillating, and wanted to identify that with the electron. I don't know what motivated that question, but what he found was that the first excited state of a spherical membrane had a mass that was 53 times the mass of the electron, and he hypothesized that could correspond to the muon, which, well, has a little more than twice that, 2.5 times that mass, but maybe that's in the details or something. That model never gained much traction. It was shown, well, maybe 20 years later that these configurations are unstable against quadrupole radiation. So those didn't really go anywhere, but they're the first membranes. This is not a string theory. The topology of fundamental string is either an open string or a closed string. So this sweeps out the cylinder and this sweeps out a plane. So the topology of the world sheet is either R2 or a cylinder, whatever you call that, R cross S1, I guess is what you would call that topologically. So, so that's a different theory. The first true string theory was due to Nambu, and shortly after elaborated by Goto. The two of them in, I think it was about 67 or 68. I give the reference here somewhere. Formulated this minimal area idea. Now, to see, let's see, to understand how you characterize area, we just have to remember the cross product. Okay, so if we have a flat surface spanned by any two independent vectors, you know that the cross product of those gives the area of the parallelogram defined by those two vectors. Now we pretty much want to make them infinitesimal, but let's look at the form of this just to get an idea what happens. You can write this cross product as the I component of this with uj uk, writing the cross product in components, and that's a half epsilon I jk uj vk minus uk vj. And you see the anti-symmetrization of the components of the two vectors is what essentially is giving us the area. This epsilon only exists in 3 dimensions. So turning that anti-symmetric product of two vectors into a third vector normal to those two happens only in 3 dimensions. But if we want the area, that's going to be the square root of u cross v dotted with u cross v. And I suspect I've left it as an exercise for you to show that expanding that turns into u squared v squared minus u dot v squared. So the area depends only on the lengths of the vectors and on their inner product. And that's something that we can write in any dimension. Now, let me see how I did this. We have a couple of differences. What we need to find the area of a curved world sheet is an infinitesimal area. And it's easy to do as a wedge product of differential forms. It's really a 2-form, but I want to come at this a slightly different way. Now, what we have, let's see. Now, if we choose adapted coordinates, I just want to see that I'm doing this coherently. We choose adapted coordinates for positions on the world sheet. So we've already said we can have sigma and tau as 2 coordinates. What I want to do is choose coordinates for our n-dimensional spacetime to be sigma and tau, and then n minus 2 other coordinates. Let's call them x, a. So there are n minus 2 of these, but we choose our coordinates so that the first two span the world sheet we're interested in. And now, what we want to do is to find a metric on that world sheet, right? You guys have had some general relativity. You know that the volume form in general relativity has a root minus g d4x, right? That determinant of the metric actually tells you how to form proper volume. So if I wanted to find the volume of some region in spacetime, I could use any coordinates as long as I put the determinant to the metric here. This quantity is tensorial. We want to do that. In order to do that, what we need is a two-dimensional metric on this submanifold. And that's not too hard to write if we use these adapted coordinates, because in terms of these coordinates, we know how to find the metric. Okay, now let's suppose we're in some space-time with metric eta mu nu. So have a metric eta mu nu, and we want to write that in terms of some generalized, some general coordinates. And let me just be clear which ones are so these, I'm going to call these capital X, and reserve small x for Cartesian coordinates in the flat metric. Then the transformation between the curvilinear coordinates, beta, it's a covariant tensor. It's a covariant rank 2 tensor, so it transforms with two factors of the Jacobi matrix. The Jacobi matrix is just built out of the partial derivatives of the one coordinate system with respect to the other. And these guys are our flat space coordinates, and these are these curvilinear coordinates. Okay, that's not so bad. We know what eta AB looks like. Now, what we want to do is restrict this to the first two coordinates. So g mu nu with mu and nu equal 1 or 2 is what I want to call hij, where now I and j run 1 to 2. And that is going to be, let's see, yeah, so hang on. I think I've gotten to my curvilinear, oh, sorry. I want these to be the curvilinear coordinates, and I want the capital X's to be the flat coordinates. I got it exactly backwards. Sorry. These are the these are going to be the flat space coordinates, the Cartesian ones. These are the curvilinear coordinates. That'll give us G in the curvilinear coordinates. So the metric on the first two curvilinear coordinates will be eta alpha beta partial x alpha d. Let's let sigma I be sigma and tau. So with respect to sigma I, dx beta d sigma j. And now we have the metric on our world sheet in terms of partial derivatives of the coordinates of the Cartesian coordinate position vector of the string. So we can write that a little more simply. Hij is equal to, all right, just the Cartesian inner product. So I'll just use that to lower one of these indices. sigma I d x alpha d sigma j. And that's now the metric. And now a volume form in 2 dimensions is an area. So the area is going to be the area of the whole worldsheet is the integral of what? The determinant of the absolute value of the metric. This is going to be a Lorentzian signature, -1 plus 1, because we have a time-like direction here, times d sigma and d tau, integrated over 2 coordinates on the worldsheet, and the square root of the determinant of the metric. So what is that determinant? Well, that's not hard to write. Hey, you guys with me? Let me take a breath here. And you all right now? You're good? Okay, so we found the metric in terms of Cartesian coordinates, identifying the position of the worldsheet. And now we just need to write that determinant. And we're only in 2 dimensions, so we can be explicit. The determinant H, Hij, is just H11, H22 minus H12, H21. And we know what those are. If we let, which way do we want to do it? Let's let sigma 1 be tau. So we have the x alpha, the tau, the x alpha, the tau. For H11, H22 is the x beta d sigma, the x beta d sigma. And then we're going to subtract the inner product of these, the tau with the x alpha d sigma, sigma. And we just get that squared. This is 1, 2, and 2, 1 gives us this squared. And look what this is. This is u squared v squared minus u dot v squared. It's the same expression that we came up with for the area of our flat space in terms of the vectors. But now we've made it an infinitesimal area so that we can integrate it and find the total area of the worldsheet. And it's convenient then to write this vector as x alpha dot, and the other one is x alpha prime, and to suppress the inner product. So to write this as x dot squared, x prime squared, square root minus x dot dotted with x prime, quantity squared, d sigma, d tau. And that is the area. And if you vary that, you're going to get the wave equation for x. So there's no magic here about string theory. You hear all these very arcane terms about what people are doing, periodic string and Calabayau spaces. But the starting point is, hey, you just write an action for a worldsheet. Now you quantize that, right? So, well, okay, we got a lot of steps here, right? There's a lot to go through, and picking notation is going to be helpful. If we choose null coordinates instead of sigma and tau, that's going to simplify some things. But this is the basic Nambu-Goto action for string theory. Now, it turns out that there's a simpler form of the action we can use. If we go back to this expression in terms of h, then remembering that h is given by those partials over there, we notice that, okay, let's see now. How do I do this? We need, right, so if I take a contraction of h with h, this is inverse to that, so I get a Kronecker and I sum on that, and that's 2. All right, but I can write this H in terms of X alpha, the sigma I, the X beta, the sigma J, contracted here. And now that means that, well, let's just divide by 2, and I have a very elaborate expression for 1. And I'm going to put that 1 in here and write A as 1/2 Hij dx alpha the sigma I dx alpha the sigma j. We still have determinant of H, and we're integrating over the overall sigma and tau. And this form of the action is called the Polyakov. Polyakov action, because it was developed by Tensor and Zermino, and independently by Brink, DeVecchia, and Howe. It came to be called the Polyakov action because a decade later, Polyakov used it in quantizing the string, and it works really well for quantizing the string. So it's a nice form of the action. It's easier to use the Polyakov form to get the equation of motion too. What you do is to treat H and X as independent variables. So we're gonna. This is a lot like the Palatini variation of the Einstein-Hilbert action, where you vary the metric and the connection independently. Here, it turns out to be very convenient to vary H independently of X and get a second set of field equations. Since there are no derivatives of H in this, there are no dynamics for H itself, except those induced by the motion of X. So that all works. In any case, you can show that the field equations you get from this expression are the same as the field equations you get. Right, this one is the Nambu-Goto action. So let's do these variations. Then let's see, we might want to introduce some constants here. So instead of 1/2, the Polyakov action has a 1/4 pi alpha prime. It's just some other constant. You can think of, alpha prime as probably, what would it be? The square root of the mass per unit length over the tension, but it's just a parameter that describes our string. So we have this constant. It's called the slope parameter. I'm not sure what it's the slope of. It's probably the slope of something when you plot string stuff. No, okay. Ready to vary the action? Okay, all right. Is it hot there? It's hot here. Yeah. Yeah, if you need a break to get some ice water, go for it. That's fine. Just let me know. It's as hard as it is to get up and give a 2-hour lecture in this heat, it's probably harder to sit and listen to a 2-hour lecture in this heat. So, anytime you want to break in and say, hey, how about them Cubs? That's fine. It's just, I understand the need to break it up. Okay, so varying this, we're going to get two things. We're varying the Polyakov action with respect to, well, x and h. Okay, so the variation with h, right, that's the metric, right? This looks like the scalar field theory where you've got, okay, this alpha runs over the n dimensions of your embedding spacetime. It looks like you've got essentially n scalar fields with no potential. It's going to give a simple wave equation. That's like a Klein-Gordon action with no mass. So if I vary h, I get 1 over 4 pi alpha prime, and just there's del hij with these partials. And root minus h. And then the variation of the determinant of the metric with respect to the inverse metric is -1/2. And this is something that you probably went through in general relativity, or didn't, but could. But you can read it in Weinberg, who just died yesterday. Did you guys see that Weinberg died? Weinberg was convinced that he was going to see the emergence of a final theory, of the ultimate theory that described everything. And he spent his career working to find such a thing. I don't know what would make anybody think that, but Weinberg was seemingly quite convinced, but made large steps along with Abdus Salam. They won the Nobel Prize for the electroweak unification. An accomplishment that that's as good as Maxwell and Maxwell's equations, right? We have successfully unified our understanding of the electromagnetic and the weak interaction. There's one interaction there, described as an SU2 cross U1 gauge theory. And what we've just gone through in the last sets of lectures. Two remarkable people, actually. I had the good fortune to meet them both on different occasions. I've heard Weinberg give talks. Just ruddy face, a little stocky in his middle age, but very enthusiastic, very bright guy. But I have a more personal story with Salam. I went to a meeting, a workshop, a 10-day workshop in Trieste, Italy, on supersymmetry and superstring. My advisor sent me to this in 1984. And well, the head of the institute, there's an international research institute in Trieste, the ICTP, International Center for Theoretical Physics, and the head of that is Salam. And my advisor, Peter Freund, said, give my regards to Salam while you're there, which meant, I had to, make my way up to the upper echelons of the institute and, knock on a door and say hello to Salam, which I did, and gave him my somewhat nervous greeting. And he remembered me. Yeah, I didn't remember that I'd heard him give a lecture 5 years before, when I was a master's student in relativity at the University of Maryland. He had come to U of Maryland and given a talk. And I don't know, I must have asked a question, right? But he remembered me 5 years later, just some graduate student from U of Maryland, just sharp mind this guy had to recall that sort of detail. He, like a lot of these people, I mean, Nambu, Desert, you know, Freund, Weinberg, so on. They are all very bright, very broad-minded people. And it is a delight to encounter and sometimes have the chance to work with. You know, really, really far-ranging thinking. You know, terrific folks. So, not that. We're varying in action here. What do we get? Right? What happens when you vary that determinant is you get it back, root h, times h times the variation of h inverse, actually, like this. And of course, you still have all of this, which I've not left space to write. So here we go. We still have h, let's call it mn, dx alpha d sigma m, dx alpha d sigma n. So we get that. Well, and we factor out this, and we can factor out the volume element. And the thing that is left is dx alpha d sigma I dx alpha d sigma j minus 1/2 h times this trace thing, mn dx alpha d sigma. This is all two-dimensional. So, in fact, a lot of string theory stuff is very easy because it's two-dimensional. Anyway, this is called the stress energy tensor. The variation of the reaction with respect to the metric in generalized coordinates gives you the energy tensor. And so this is the energy tensor, but because we're treating h as an independent variable, that vanishes. And we have what turns out to be a very useful constraint in addition to the field equation we get from the variation of x. Now, notice that this is automatically traceless. If I sum ij here, then with an hij here, I'm going to get a 2 that cancels this, and the two terms cancel. So this is a traceless stress energy tensor, and that's a signal of conformal invariance in the theory. Now, conformal invariance here isn't too hard to see because if I rescale the variables, you find that, well, here's the action, that this action is invariant under rescaling as well. So among the symmetries, and there are several symmetries of this action, I'll talk about them in a minute, but let me make a note. But first, let's find the other field equation. I'm going to vary this, so I'm going to get variation of x. It's going to give me a 2 I alpha prime. And I'm just going to get 2 of the same factor because this is symmetric. So we'll have hij partial x alpha partial sigma I times partial del x alpha del sigma j. We just get 2 of those. That's why the 2 here. And then we still have the root h out here integrated over sigma and tau. So we integrate by parts. By alpha prime d sigma j of hij root minus h dx alpha d sigma I times del x alpha d2x. And if I multiply and divide by determinant h, like this, then do you recognize that? That's the field equation. Let me write it. 1 over determinant d sigma j of root Hij x alpha d sigma I equals 0. There's our field equation. Now, do you recognize this form? Where is it there?
Sorry, can you point that out again? My computer froze up for just a second.
Yeah, here.
Okay.
This is 0 here. But okay, 1 over square root determinant, partial derivative of square root determinant times the, well, this is just raising that partial to a contravariant vector. Do you recognize the divergence theorem from general relativity? Right, where you have 1 over determinant partial alpha root g of some current, say 0. That would be the covariant divergence of the curve, right? The divergence theorem from general relativity holds here too. We're just doing, curvilinear coordinates in 2 dimensions. The same results hold. So this is the covariant derivative of, all right, that partial is also a covariant derivative. And so, I guess I can put it up here. What we have is the wave operator. We have di x alpha equals 0. That's just the covariant wave operator on x equals 0. So, like we had for just the classical string, between 2 endpoints, the equation of motion is the wave equation. Now, the difference here is that we have n different modes of oscillation of this thing. This can oscillate in a whole bunch of different directions. But other than that, it is just oscillating. So we have this energy constraint, and we have the wave equation. So now let's look at symmetries, because we can use the symmetries to simplify this a great deal. Are there any questions on getting the field equation? We're good there? Okay. So there's our action. And let's keep the action in right at the symmetry. So so we have conformal, which means that we can replace h by a scalar times h for any scalar, and the theory remains the same. So we can rescale h by a factor. Then we have, all right, now this alpha contraction is done with the Minkowski metric. We're in a flat background space here, but we still have global Poincare transformations. How do we see we have global Poincare? Well, we have global Lorentz transformations because this is a Lorentz scalar in that larger space. We also have translational symmetry here, and we can see that in 2 ways. If I translate x by some constant, all right, you just have derivatives here, so that constant goes away. So it's invariant if we replace x by x plus some constant vector. The other way to see that is to notice that x itself is a cyclic coordinate. X only its derivatives occur here, and so its conjugate momentum is conserved. So momentum is the translation generator, and so gives rise to this symmetry. And then we have general coordinate invariance in 2 dimensions. So sigma and tau can be replaced by any two convenient parameters, and we're still talking about the same theory. So let's see. Now, Eli, you wanted to stop at 4 today? So is that right?
Either 4 or 4:30ish.
4:30. Okay. All right. So yeah. So let's. I know we started at 2:30, but let's wrap it up by 4:30 then. So pressing on with this warm day. Okay. So I want to use the conformal symmetry and the general coordinate invariance here. This allows me to replace x by, or more generally, I can replace x by a Lorentz transformation on x plus a translation by a constant vector. Those are independent of sigma and tau. Those are global transformations, not local. But we have a lot of power in these two. Let's have a look at it. That metric gives us a line element. S squared is hij dxi equals sigma I d sigma j. But let's just write it out. We've got some function a, dependent on the sigmas. These are functions of the sigma I d tau squared with a minus sign. And we've got, let me put a 2 here and some other function d sigma d tau. There could be a cross term, and then we could have some c of sigma and d sigma squared, and that's the most general two-dimensional metric we can write. And what I want to do is, excuse me, just choosing the answer here. I could make this arbitrary and determine what we need, but what I want to do is let some function f times d tau. This is a new tau. Let's call it tau tilde. Defining a new tau be given by a linear combination of sigma and tau. So let's let it be, and let's make these squared. There. So a times the original d tau plus some multiple of d sigma, and the one that is going to work, so I might as well just go ahead and use it as minus b over a times d sigma. So now, in terms of this new coordinate, I have f squared d tau tilde squared minus that, right? So ds squared is equal to, so let's see. Now, let me write this out first. Minus f squared d tau squared is equal to minus a squared d tau squared, which gets us this first term. And then we get a cross term, minus becomes plus because of this sign, 2b d tau d sigma, then minus b squared over a squared d sigma squared. So I can write that I can write the first two terms here as the sum of this and that. So I can write ds squared is now minus f squared d tau squared. And then we're going to get, bring this to this side and it's plus. So we have plus b squared over a squared plus c squared. Let's see, minus that is minus, no. This puts, is this minus or plus? Let's see, minus f squared can't think, right? It's something times d sigma squared. this is plus or minus, which way does it go? I took a minus here. That sign goes away, so I get plus, but I'm taking minus the square, so I have a minus here. So if I bring this to the other side, b squared over a squared plus b times d sigma squared. The first two terms are equal to this, so it's just plus. Okay, so that reduces the equation to this, where I get to choose f to be anything I like. Well, I'm going to choose f to be b squared over a squared plus c squared, which means that let f squared equal b squared over a squared plus c squared, and that tells me that the s squared is just f squared times minus d tau tilde squared plus d sigma squared. That's a conformal transformation. So since I can replace h by any multiple of h, I can choose that multiple to be 1 over f squared, and I'm left with the Minkowski metric as the metric on the world sheet. So I can choose my coordinates and my conformal factor to make the world sheet have a flat metric. And that means that in my field equation, I can take hij to be just the Minkowski metric in 2 dimensions. hij is just -1. And that simplifies a whole lot of stuff really quickly. Now, let's see. What do I want to show next? Yeah, we can use this to simplify that energy constraint. Let me not do that quite yet. Let's write the field equation first, because that now becomes very simple. So making all these choices, we have 1 over determinant of minus h dd sigma I of, used to general relativity here, I keep writing g, then this would be the partial I of x alpha. 0 is equal to that, but now the determinant of h is just -1. The volume form always has the absolute value of the determinant. So these factors are just 1, and we just have eta ij di dj x alpha equals 0. And that's easy to write out. This is dx alpha, d squared b tau squared plus d squared x alpha sigma squared equals 0. So we have a simple wave equation. Of course, there's the speed of light sitting here. The string moves with the speed of light. And now what? I guess we solve that. Yeah, now I've been working on the best way to write this. But, it's not hard to solve that equation. There are two kinds of things we can write. So x of sigma and tau. Okay, so we have an initial position. So we have the center of mass motion. Starts at an arbitrary position, moves with some constant velocity, which I'll write as 1 over m p0 alpha times tau. So there's the center of mass motion. Everything else is oscillations. So what we can write, and I'm not sure the best way to write this, but let's just do a general Fourier series here. Let's let n run from minus infinity to infinity, and take some alpha n mu. Then I want to take, now I have to make one of these things, yeah, e to the I and sigma plus conjugate, either minus I and sigma, all times e to the I and tau. Sorry, can you see that? I squished it in there. Since I'm summing over positive and negative n, that's going to give me all the modes of the tau. And then I've written the spatial modes independently this way. So the only thing I want to do, let me call these beta. Sorry, mostly because I want to change them to alpha in a minute by pulling out some constants. There are a couple things. Beta 0 mu, for n equals 0, that's 1, that's 1. Everything's 1 except this bit, bar mu. This is just some real number. So I can add that into the initial position. So let's handle the 0 mode just by shifting the initial position. So I can write sigma tau as some new initial position, and now I've handled the 0. Then I want to change the name of 1 over m to L squared for reasons I'm afraid I don't remember, but I can with L just some convenient constant, perhaps square root of 1 over m. And then for the series, I want to pull out a couple things. I want to pull out an IL, just a different constant. It's the same constant, but 1 power instead of 2. And then the sum, what I want is, all right, n equal minus infinity to infinity, but not equal to 0, like this. And then a factor 1 over n is convenient. And so beta, I just want to let beta be alpha over n. And that helps out in a couple of different ways. E to the I and sigma plus the conjugate alpha bar mu and e to the minus I and sigma times e to the I and tau. And so there's my general solution for the string. Okay. Nothing magic here, nothing particularly difficult here. We know we can write the solution like that. Now, notice all the constants here, all the mode amplitudes. When we quantize, all right, we put a hat on this. This becomes an operator. So we have a position operator. This momentum becomes an operator, and each of these alphas will become an alpha hat and an alpha dagger hat. Those mode amplitudes all become operators. So we have some huge quantum algebra going on here, and this is really the fact of all these modes really underlines the power of string theory to describe many different particles. Okay, if you have a string oscillating in some high energy mode or some low energy mode, okay, those have different energy, so they have different mass. And because we have an infinite number of modes, both for alpha and alpha conjugate, we have an infinite spectrum of possible excitations of this system, which will correspond to different mass particles. Okay, the more excited the string, the more massive the particle that it will be interpreted as. Now, the length of these strings is perhaps Planck. You know, these are extremely short. You know, they look like particles. You encounter a string, oh, that was a muon or something. You know, a quark. These things we'll see in point-like in many kind of experiment we've done to date. But this is our basic solution of the string wave equation. Now, the energy condition, all right, it's traceless. The energy tensor is a symmetric 2x2, so it has 3 degrees of freedom. It's trace-free, so there are 2 degrees of freedom. So we get 2 constraints from the vanishing of the energy tensor. And those end up being, basically a condition on the norm of all these guys. There's some squared norm of those that we'll have to basically give a constant. It's more or less a normalization condition, and we'll encounter that later. But the other condition that we need is reality. This is a real n-dimensional space-time vector. So let's look at the consequences of reality for that. Now, those right, you solve this equation. Right now, that doesn't give us a unique string. In addition to the general solution, we need boundary conditions on the string. So we'll get the boundary conditions time permitting. Let's see how much we get to today. But let's see. Reality, okay, initial position, velocity, those are already real. So we need reality of this sum. If I take the complex conjugate of that, I have minus IL, sum on n not equal to 0, 1 over n, alpha n mu e to the I sigma, I n sigma. The complex conjugate gives minus I n sigma and alpha bar here. Then alpha bar becomes alpha and e to the I n sigma. And that has to equal the thing we start. Whoops, I forgot my tau. Minus I n tau has to be equal to I L sum 1 over n alpha n mu e to the I n sigma plus alpha bar n mu minus I n sigma e to the I n tau. Okay, so now I can get rid of this IL. I'd like to get rid of the sum because these have to match term by term, except I have to be careful to include both plus and minus n. So for any n, what we have is 1 over n alpha bar n mu e to the minus I n sigma plus alpha n mu e to the I n sigma. Plus, we're summing over plus and minus n here, so we also have minus 1 over n, or 1 over minus n, and alpha bar minus n mu e to the plus I n sigma plus alpha minus n mu e to the minus I n sigma. So all of that has to equal a similar thing on the other side. Let's keep our solution here. Okay, so on the other side, 1 over n alpha n mu e to the I n sigma plus alpha bar n mu e to the minus I n sigma e to the rats. I lost my e to the minus I n tau over here, and on this term it becomes e to the plus I n tau. Okay. E to the I n tau, and the same thing with minus n alpha minus n mu e to the minus I n sigma plus alpha bar minus n mu e to the I n sigma times e to the minus I n tau, and I need a bigger board. Okay, so now we collect terms, and things that better go together. So let's collect all of the e to the I n tau terms. Let's see, this is e to the minus I n tau, that's e to the minus I n tau. So let's see. All right, we can get rid of the 1 over n's now. We've taken into account n minus n, so we don't need those anymore. So we have minus alpha bar of minus n mu e to the I n sigma plus alpha of minus n mu e to the minus I n sigma. Then on this side, we have these terms. Bring them to the other side, so we have minus alpha n mu e to the I n sigma minus alpha bar n mu e to the minus I n sigma. I'm going to make all of this equal to 0. Then we have the conjugate modes for tau times what turns out to be a very similar thing. Let's see, we're going to get these guys. So alpha bar n mu e to the minus I n sigma alpha n mu e to the I n sigma. Then bring this to the other side, it becomes plus alpha minus n mu e to the minus I n sigma, and let's see. That one should have, there's a minus, so this one should have been minus. Finally, this term minus, bringing it to the other side becomes plus alpha bar minus n mu e to the I n sigma. All of that equals 0. So this stuff has to equal 0, that stuff has to equal 0. But notice here we have alpha bar and alpha minus n. Those two are independent of these two. Those two have to cancel. Here we have the conjugate of the same thing, alpha bar of minus n with alpha of n. Basically, you can write this whole thing as alpha n bar plus alpha minus n mu times stuff. And that stuff is not always 0. Here we have the same thing. Everything has minus signs, but the plus I n sigma, it's the sum of the same two things. It's the conjugate of minus n with the unconjugate of plus n, or it's alpha minus n with the conjugate of n. The conjugate of this is equal to that. So we get the same thing from all 4 independent combinations. And so we have alpha bar n equal to minus alpha of minus n mu. And that's a different sign that I came up with this afternoon. So let me check what I've done here. Why did I get a different sign? Let's see, minus n, let me just, okay. Where's the minus n? Did I lose a complex conjugate? I may have lost this sign. So here, 1 over n, this is all of that, but I lost that sign. So I should have had minus plus. That's going to change half the signs and make that a plus. So exercise. Do it correctly. This is in the notes, and I think I worked it out this morning actually, and got it this way. That's actually one reason for including the I here in the first place, is that it makes these two equal. So let me try and carry this sign through. This is the first stuff. So minus. Okay, which values are these? E to the I n t. So I did this one first, and so those should have been pluses here and here. Yeah, and you can see already, without changing the other half that come from the other half here, now we have alpha bar mu of minus n equal to alpha mu n. With the minus sign between, here's a minus sign between. Then here we change these two signs, so those two are minus, and now we have a relative minus sign here times arbitrary Fourier modes, or what stuff refers to. So, if we take the conjugate and replace n by minus n, we're talking about the same thing. Oh, hello, and we've got a visitor. Yes, we've. Now, if you think it's warm today, try holding a cat. So let's see. That gives us alternative ways of writing our expansion. Now, for the most part, we. Hey, come on. Writing it this way is standard form. Now we need to impose boundary conditions. So boundary conditions, there are two basic kinds we mentioned, the closed and the open boundary conditions. But those break down further. So the boundary conditions we can use for closed string, so this boundary conditions. For closed string, what we need is for x alpha at sigma and tau to be the same as x alpha at sigma plus pi and tau, for all tau. So at any time going into the string, you come back to the same point. And I've chosen to let sigma run from 0 to pi here. We can absorb any additional constants in our parameterization. Remember, we can use any parameter sigma and tau we like. So let's just choose them so that they run from 0 to pi. All right, that's all we can do for the closed string. For open string, we have Neumann boundary conditions. Right, that's a condition on the derivatives. So d sigma d tau at 0 and tau has to equal the alpha d tau at pi and tau for all tau, and a similar condition for the sigma derivatives. Wait, let me double check myself on this. the Neumann conditions. Now, haven't worked through the open string here yet. No, it's yeah, dd tau can be anything. It's just dd sigma that we're interested in. And so we want no motion. We want no longitudinal motion of a string, right? So our Neumann condition is there's no change of the endpoints. The derivative in the longitudinal direction of the endpoints is 0. So that's our Neumann boundary condition. We can have Dirichlet conditions. And that tells us that x alpha at 0 and tau should be some constant and some constant vector, and x alpha at pi and tau should be some constant vector. So we need to work out these boundary conditions. While looking up boundary conditions, I encountered an interesting thing. The there are other boundary conditions, and you see this in the early chapters of Jackson's electrodynamics book, where you also probably learn about Dirichlet and Neumann boundary conditions. It's possible to mix them, and Jackson does an example where you've got a plane with a hole in it, and in the region of the hole, you put a condition on the function on the value of the potential, but out at great distances, you want a condition on the fields, and so you have some Neumann type condition on the derivatives of the potential. And so for one part of the boundary, you've got Neumann. For another part of the boundary, you've got Dirichlet. That's possible, but there's something called Robin boundary conditions, where you take an arbitrary functional linear combination of Neumann and Dirichlet, and that still uniquely determines the solution. Now, Jackson says of this, piecewise Neumann and Dirichlet, that basically that field is not well developed because, well, it's hard. It's hard to impose that. You get two independent integral equations you've got to solve, and it's just pretty nasty, really. But for nice enough situations, you can solve that. He doesn't even mention Robin boundary conditions, but they've been around since the 1800s, and might be used in some engineering applications, and probably situations where you are going to put it all on a computer anyway. But there's an interesting conjecture, is that if you apply something like Robin boundary conditions, the most general boundary condition, to the open string, you're basically introducing a whole extra parameter into the theory. And it could make your 10-dimensional theory effectively 11-dimensional, which is what people have done in M theory, where different types of string, which originally had to do with different boundary conditions, but now that they have to do with topological considerations, or have to do with that as well, and they apply to the superstring. So there are a lot of complexities here to investigate, but it does make me wonder whether the equivalence of these different string theories might be overcome by using Robin boundary conditions from the start. And then as special cases, you get the Dirichlet or the Neumann boundary condition, but parameterize things in between and perhaps that would give a way to see the unity between the different string theories that people use. As I say, there are other complications there, because in order to do a superstring, right, we're going to see that when we quantize this and use these mode operators, okay, these get hats on them. So you've got alphas and alpha daggers as some quantum operators. There's a quadratic form in these alphas that have a commutator that can give the Lorentz algebra, but it's got an extra term in general. That extra term depends on the dimension of the space you're in. And, it ends up being basically d minus 26. So if you do this theory in 26 space-time dimensions, then that extra term drops out and you get the Lorentz algebra as a consequence of the quantized string operators. Now, in order to talk about superstring, you have to redo that calculation. And what seems to be happening, at least is conjectured to happen, I'm not sure the exact state of this now, but the superstring looks like a compactification of the bosonic string. That is, if you compactify 6 dimensions on some very symmetric space, that gives an internal symmetry to a 10-dimensional string. And it's that 10-dimensional string that can be supersymmetrized. And the size of the symmetry group of, say, a 16 sphere or some maximally symmetric 16 space has the same dimension as the internal symmetry of the superstring. I don't know whether anyone has actually showed this result, that is in fact what happens, but it could be.
So we just lost Eli.
Sorry, what? Oh.
So we just lost Eli.
Oops. Oh, okay.
Sure, he'll be right back.
I imagine he'll be right back. Anyway, yeah, so I don't know if that's exactly the case or not, but in any case, in order for the superstring to be consistent, you need to formulate that in 10 dimensions. And people still talk about there being 5 types of string theory, but the types are different than they used to be. They used to be type 1, type 2A, type 2B, it's more complicated than that now, because we're talking about 5 types of superstring in 10 dimensions. One of them has an internal symmetry of SO32. The other has an internal symmetry of E8 cross E8. But remember these dualities I talked about, where you expand in different parameters, or you interchange certain position and momentum information. Each of those string theories is related to each of the others by some string of these dualities. So yeah, here comes Eli again. Welcome back.
Gotta love computer issues.
Yeah, well, that happens. Yeah, I was just saying how the issue of the different string types, you might overcome it by generalizing this boundary condition, or might not, I'm not sure, but to investigate it's hard, because you really want to talk about 5 types of superstring. The 5 types of superstring are related by these dualities, by interchanging parameters, either an expansion parameter or position and momentum type things. But you know, to show whether or not those 5 types are related to the these types of boundary conditions would probably be a difficult problem. You would have to at least first gain a deep understanding of the types of superstring in 10 dimensions. So anyway, don't know about that, but we can straightforwardly look at closed strings or open strings with either Neumann or Dirichlet boundary conditions. And those are straightforward constraints on basically the range of the parameters and the relationships of the various expansion coefficients. Let's say at least a little bit about closed string, because, well, I can in the short time remaining, and I haven't worked out the open string yet, so we can talk about that. This raises an issue. Let's see. Well, Alex had to be out of town. How much longer do you want to continue with these lectures? You know, we're coming up fast on the formal end of the semester. We're coming up fast on the beginning of the fall semester. We've covered the standard model, which is a nice achievement already. You know, talking about string theory is gravy. I'm happy to talk with you know, any or all of you about string theory, time permitting, but you know, it may be getting close to time to press on with other things. Now, on top of that, I'm going to be out of town in 2 weeks, Monday, in a place where it won't be very easy for me to hold a lecture. I mean, we could move it to Friday like we did that one time and only 2 people showed up. But let's maybe have one more meeting. And, you know, I'll see if I can get through these boundary conditions and do the quantization of these modes. And I would really like to be able to develop the Poincare, the algebra from those mode amplitudes. I'm not sure if we will, you know, get through that in one lecture or not. I presented that in a series of seminars ages ago, back in, when was it? 86, 87. I gave a series of 5 lectures, yeah, which should be about 5 hours. So maybe we have time to get that far. And you know, I'd like to see that again. So I'll certainly continue working on these notes to get to that far. Let's see if we can't cover through that next Monday and call that good for now. As I say, you know, always happy to talk with you about any of these ideas. We're barely scratching the surface of string theory here. It has gone in so many interesting directions. We can pursue that, you know, outside of the Summer Quantum Field Theory Club. So then, yeah, what happens with the, let's say, the closed string, right? Now, yeah, this is actually pretty easy because we've done most of the work already. We've found the reality or we've imposed the reality to get this form. I've already chosen the constants tightly. All we have to do is make sure that this closes if we change sigma by pi. But that means that e to the I n sigma is going to go to e to the I n sigma plus pi. And let's see, so we've got an alpha n mu there. We have an alpha bar n mu with e to the minus I n sigma plus pi here. And so what's going to come out will be e to the I n pi here, alpha n mu e to the I n sigma. but then e to the minus in pi over here times alpha bar and e to the minus in sigma. And all this is inside this sum and so forth. But what this means is if I pull out this factor overall, I can put a 2 here, and that's just equal to 1. So what happens when I go to x of sigma plus pi is I get an e to the in pi here. And the only way to get rid of that is by dealing with only even n. So the closed boundary condition just takes n even here. So for x closed, and we can handle that by now, if we sum over all n, but just put a 2 in the exponent here, e to the 2in sigma and e to the minus 2in sigma, and e to the 2in tau, that effectively sums over. And then let's see, basically I'm replacing n by 2n. I believe that puts a 2 here as well. And then these alphas are some arbitrary coefficients anyway. So there we have the solution for the closed string. And then these alphas simply depend on how the string is excited. Yeah, let's see, and that becomes an initial value problem. So if we were to give the configuration of the string at time tau equals 0, then that would be sufficient to determine all of the alphas by a Fourier series, and then by simply including the time, we know the full evolution. So we basically solved the problem for the closed string. For the open string, we have all modes, but some additional conditions. You know, well, you can work that out for an exercise for next Monday. How about that? And yeah, I will too. And we'll talk about the open string solution next time, because I haven't finished working it out yet. But it's similarly straightforward. We just at the endpoints we impose some condition. So that's going to be some. Let's see. I don't think it constrains the modes to even modes. I think we can have any oscillations, but we have some condition on the initial position and momentum. So we'll get there next time. We're approaching 4:30 here, and this is as far as I've gotten in the notes. So this is a good spot to wind it down. Now, just to give a little direction. Okay, so we get the classical solutions. Now we do canonical quantization. So we need the Hamiltonian formulation of this. Then we let Poisson brackets go to commutators times IH bar, and all our mode amplitudes go to operators. And we find the Lie algebra of the mode amplitudes. Certain combinations of the mode amplitudes give rise to something called the Virasoro algebra. It's this infinite dimensional algebra. We get 2 copies of that. That's basically the quantum algebra. So we'll run through some of that. Yeah, maybe I can give some of that as exercises and state some of the results, and then put some of the details in the text so you can read through it without putting every bit on the board. But it's straightforward, but long Fourier series, so like field theory, some of the expressions get lengthy. So anyway, there's the start of string theory, and it's actually, it's just a classical system that we're going to quantize, but it's a very rich one. And yeah, I think if we can get to the Poincare algebra, I think that would be a nice point to reach. So thanks for your continued attention. I'll get this up. It always takes a little while for this to download, but I'll get the recording available. And let's see, I want to do a little bit more. As soon as I finish with the boundary conditions, I'll post the new part of the notes. We're bouncing against page 400 here. I can't believe we've gone through that much. That's a lot of writing on my part and a lot of patience on yours to follow this through. So, okay. Any questions? I can stick around, but Eli, you had something you needed to do.
Yeah, I'll be headed out here now. So
yeah.
Yeah,
So yeah.
I got that.
All right.
Food recession.
all right, have a good one, guys.
All right.
Yeah, same.
All right.
Till next time.
We'll see you.
See you Monday.